Alrighty, welcome everybody. Thanks for joining us tonight. So this week is gonna be all about embeddings. So covering the agenda today, reminders to record the meeting, join the Outlook and Google group if you have not already done so, and also keep working on your research proposal drafts. We did post, if you missed it, we posted a template, an updated template for you guys that is much shorter. So yeah, just make sure to finish that or keep working on that. Also, the surveys, if you don't have access to Pace and you'd like, please fill out the survey. And then also the 8903 interest form if you're interested in pursuing that. So today is going to be all about embeddings, and next week is going to be about information retrieval. So today is like the project number two of the three-part series of the projects that we're going to be doing this semester. So basically just covering embeddings very quickly is the only slide that I have for today. Today's going to be very hands-on. But just talking through the ideas of embeddings, because embeddings are really, really useful for many, many things. So we have data, and mostly it's either going to be images or it's going to be text data that we have. And being able to capture the semantic meaning of the data in a way that it makes sense, it's a very powerful concept in machine learning. And I don't know if you guys have heard of models like word2vec that basically takes a word and transforms into a vector representation of the word. Embeddings are basically the same concept. You're taking data and you're feeding through a model, and the model is learning a lent a latent representation of the data in a higher dimensional space or lower dimensional space. You can compress the data into a lower dimensional space. And that's really helpful because once you do have embeddings, which is just this vector of numbers, and the numbers represents the meaning of the data that you have, you can do all kinds of really cool things. You can do ranking with embeddings, you can do similarity search, you can train linear classifiers on those embeddings, you can form clusters on them, which we're going to be doing today. And it's super, super helpful. So this concept of just taking data and transforming into a vector of numbers in some high dimensional space, and data that is similar is also going to be clustered or is going to be close, geometrically speaking, in that high dimensional space. It's a really powerful concept. So today we're going to be doing that. And also just saying, I think every single lab, or at least most of them, we leverage embeddings in many different ways. And yeah, so today is going to be all about that. Um, Let me actually go here. Okay, so just like last time, on the left, I have the repo, and well, the GitHub repo that we're working from the semester. So the fall 2025 interest group projects. And then here on the right, I have my session on pace. And I'm on a GPU right now. I don't even know why. I could be doing this on a CPU because I don't think I'm going to be running anything. I already have the notebook ran, so we don't lose time. But one thing that I wanted to do is, I guess, just cover the project's README and go through the virtual environment installation again, because I think the last time I kind of covered that, but maybe it was too fast or too quick. And one thing that I did do last time was we ended up installing the virtual environment on Scratch. And remember, on Pace, we have three main directories. We have our home directory, we have the project directory, and we have the Scratch directory. Home directory only has 20 gigabytes of space, so it's very limited. We don't recommend installing or keeping things in your home directory if they're going to be very huge in size. The project directory is shared across everybody, and it's 1 terabyte. So that's where it goes off the data. Basically, home directory goes your code, project directory goes the data between all of the projects that we do. So data sets, And the Scratch directory, it has 15 terabytes, so it's huge, but it's temporary. So you can usually install like the virtual environment on the Scratch, and that's what I did on the project last time. But the issue with that is that Scratch is not as easily accessible as the temporary directory or your home directory. So if you remember last time, when I was trying to run the LoRa notebook, it took a while for the dependencies to run. Oh, actually, the notebook was already loaded, I think. I don't think I ran, or maybe I did, I don't remember. But anyway, the dependencies took a while, and that's because they were in Scratch. And basically transferring the files from Scratch to your interactive session, it really depends on the network, and sometimes that can be just a bottleneck. So today I'm actually going to be going over how to install the virtual environment on the temporary directory. And all of this is in the README under the project. So again, if you're on the repo and you go on the project folder, there's going to be this folder O2 embeddings. And here we have a notebook that I'm going to be going over. And we also have the PyProject YAML file for you guys to install the virtual environments, which I'm going to be doing right now. So here on the right, I'm on a pay session. And the first thing I'm going to do is I'm going to install the virtual environment on the temporary. And then I'm going to source it. So source /temp venv bin activate. Cool. I'm not gonna clear. I'm just gonna leave like that. The next thing that we're gonna do is, well, here I need to change that because I put my username, but that would be, and that's also wrong because he's on the LoRa, but I'm gonna be doing right now. The next thing that we're gonna do is we're gonna create a seam link between the virtual environments that we just created, the venv, and your user folder under the project. So if we go here, I installed the repo I created this folder called the sgt-arc that I'll show you. If I go here, cd -sgt, and then, so if I do a pwd, this is the directory where I clone the repo locally on Pace, right? So the sgt, that's the folder I created, and then I clone the repo inside that folder. Okay, so and if we just do an ls-la, you see that we have a user folder, we have a project folder, and we have a user folder. And your user folder has your usernames, and you can see that some people already submitted their notebooks from last time, and I did see some pull requests on the repo. So thank you very much for submitting your PRs. We're gonna make sure to go through those and accept them very soon. But anyway, just keep going with the installation. What we wanna do is the temporary directory, it's temporary to the instance that you have. So every time you terminate your instance or it just runs out of time, everything that is on temp, it gets deleted. So if you do install the virtual environment on the temporary directory, just like I did, if you create one, next time you get a new session, like tomorrow, it's not going to be there anymore because it's not persistent. So you need to install every single time. But the good side of that is that unlike Scratch, it's going to be more readily available because he doesn't have to transfer the files over the network. So it's much easy. It's much faster to load the packages that you need. And yeah, I can demonstrate that now. So basically, what we did, we just ran those two commands here to install the venv. The next thing we're gonna do is I'm gonna go to my user directory. So I'm gonna go cd users my name, And then I'm gonna create the seam link. So it's gonna be ln dash s, and it's gonna be temp dir slash venv, and it's gonna be like this, ewd dash venv. So if I do an ls dash la here, you can see that, oh, I probably did it wrong, huh? Uh, oops, ls dash la. Did you create it? Yeah, no, I think it's fine. I'm not sure why it's showing red. It's supposed to be blue, but it's fine. The next thing that we're gonna do is I'm gonna go to the projects folder. So cd projects, and I'm gonna go to the embeddings folder. And the virtual environment is already activated, so I'm gonna do a UV. Oh, let me clear. Oops. Okay, UV pim install -e. And this is going to install all of the packages. Does anybody has any questions, by the way? Feel free to ask questions as I go through. Okay, no questions. Um, I do have a question, and that's for Anthony on the call. Do you know why the seam link is showing red instead of blue? If I
Let me
go
see. Let me see it again.
um ds for user my name ls-la here.
Uh, can you do echo tmpdir? Do the variable
Oh,
the variable expansion. Uh, it might be that it's single quoted for some reason. So single quoting like prevents variable expansion.
mm,
So you could try relinking it again, just rm.venv and then uh, just no dash r, just rm, yeah, and then symlink again. So
okay,
ln dash s,
yep. And
the
then
tmp dir, whatever
yep,
the name was it. Yeah, so there it's like backslashing.
I
Um,
see.
and when you backslash the variable expansion, then it's gonna treat it like a string instead of expanding it.
I see. Okay, that's solved. Thank you. Cool. Thank you, Anthony. Okay,
Yeah.
so going back to the installation, we finished installing our advanced there, and we also seam linked it to our user directory. I'll make sure to update the README here to be more clear. I literally did this a few minutes before the meeting today. But okay, I just wanted to show you guys how that's done. And then the other thing that I wanted to show was, well, now we do have the virtual environment. The thing that you're going to be doing for this week is that you're going to be heading into the O2 embeddings folder, and there's going to be this embeddings notebook. And the notebook, as you can see, it's not run. Like it doesn't have any outputs. So what are you going to be doing? You're going to be basically copying this. So you copy, and then you're going to go under your user directory, and then you paste it. And I already have mine here, so I don't need to paste. I'm just going to open mine. And mine is already run. So as you can see, it has some outputs on the notebook, and I'm gonna go through them today, like right now. So to connect the notebook to the VM that you created, again, you can click here on the upper right corner, and then you're gonna do select a kernel, Python environments, and I don't think this is the right one that we created. So the thing that we're gonna do is do Command Shift P or Control Shift P if you're using Windows, and you're gonna go on. You're just gonna type Python and then select interpreter, and you're gonna go enter interpreter path and browse, and you're gonna go to the directory that we are currently because I seen linked it. You should be able to see the vent in your users folder where you're running the notebook from. So I go, oops, I did it too fast. You go on venv, then, and then Python 3.10. And when you go here, select another kernel, Jupyter Notebooks, and you refresh, you should be able to see the one that is under, and you're going to be able to see user, your username, and there's going to be a little star here on the venv. So that's how you select the environment. And I guess just to show you guys how much faster it is to load, I mentioned that last time when I tried to load all of the dependencies, especially Torch, since it's a heavy dependency or a heavy library, it took like 4 minutes. So because the virtual environment right now is under the temp directory, it should load faster, but it's not even running. Import storage. Okay, let me just wait a few seconds. Does anybody has any questions? Okay, we have a question. So is the symlink just a way for us to download dependencies into the temp directory to the venv? No, the symlink is it means symbolic link. So it's a way for you to sync basically a folder. In this case, we're syncing the virtual environment because the virtual environment is stored in the temp directory, right? So if you want to have the environments available under your user directory, like basically it's just linking into the temp, but it's available under your user. So for example, if I want to, um, let me do let me do, go back to the,
Yeah, another way to
well,
explain it too while you're kind of doing that is the symlink is a pointer. So like you have a pointer to the virtual environment directory that's in the temporary directory. Yeah. Yeah, so
yeah, exactly. So instead of, for example, if I do deactivate and I deactivate my environment, um, instead of activating through the temp directory or having to go in the temp directory, I can just go on my user directory and then I can activate it from here, uh, like this. And it's just easier, like especially if you're running the notebook from here, or if you're running something from whatever directory you're running from, it's just easier to have that virtual environment available in that directory. So the way how we would be using this, for example, for the research would be I have my own environmental base. I would be creating the venv on the temp directory, and then I symlink into the root folder of my project. In that case, I would be symlinking into the fall 2025 interest group instead of my username. You can also do on your username, that's totally fine. Um, but it's just like Anthony said, it's just pointing to that folder on temp. Um, yeah, cool. Okay, I have no idea why it's taking this long to load, but good thing that it's already loaded. So yeah, let me go through the notebook itself. So basically what we're going to be doing here today on the embeddings. So we're going to be doing extracting embeddings from a vision transformer model, specifically Dino V2. We're going to be doing some clustering with those embeddings and seeing how those images are similar to one another um, on this high dimensional space. And we're going to be doing some similarity search with k nearest neighbors. So basically, once we do have those vectors, we can basically see how similar they are by the cosine distance. Or in this case, it's going to be k and n, so it's not cosine distance per se, but you can do like cosine similarity between vectors. So yeah, just going through the notebook. So fashion MNIST is basically an evolution of the MNIST dataset. I don't know if you heard about the MNIST dataset. I think I have it here. Yeah. So is this kind of quintessential data for image classification? It's a very old dataset. Yeah, the image is super tiny over there. But it's basically this data set that he has handwritten images, and it's one of those basically toy data sets that you play when you are first starting to do any kind of computer vision. But back in the time, it was actually a really hard problem to solve, like how to do digit recognition. So the data set is images of numbers, and it goes just numbers from 0 through 9, and it's only one number per image. And as a follow-up of the data set, and let me actually make everything a little bigger now. As a follow-up of that, they created this fashion MNIST data set that is, it has the same idea. It has 10 classes or maybe a little bit more, but it's pictures, very low scale or low resolution pictures of images. So the fashion MNIST data set contains 70,000 grayscale images. Each image is only 28 by 28 pixels, so super tiny. And it has 10 different clothing categories. And the data set kind of looks like this. And if I click here, you're going to see that that's the official fashion MNIST repo. And they already have like some kind of clustering here, just clustering all of the clothes together in this three-dimensional space, which is pretty cool. But going back to the data set, that's basically it. And you have the training set and a test set. The training set has 60,000 images, and the test set has only 10,000 images. And today we're just going to be using the training set for doing all of the clustering and the nearest neighbor search. So yeah, understand the data set, like I said, he only has 10 classes. So t-shirts, trouser, pullovers, dress coats, sandal shirt, sneaker bag, and ankle boots. So those are the categories of the images that are in the data set. So basically this, we're just loading the data and then we do a transformation. We basically load the data into tensors and then we normalize the data because grayscale images are just images itself. Pixels, they range between 0 and 255 in their intensity. 0 meaning they're completely dark, and 255 they're the brightest intensity that there is. In a grayscale format, which I'm going to be talking about, 0 is completely black and 255 is completely white, and everything in between is just a range of it's basically a gray scale from very dark gray to very light gray, or basically almost white. And we normalize because in machine learning, models usually like tiny normalized numbers. They basically converge better, and it has a bunch of nice properties during training. But here we're just loading the data. So you can see that the train images shape, yeah, 60,000 images. This one is the channel. So like I said, it's a grayscale image data set. The one channel just means it has just one, the one it just means it has one channel. So It's a grayscale. If this was RGB, if he was colored, he would be 3. And then 2828 is the size of the image. So 60,000 is the entire size of the entire data set, like the number of images on the data set. And then the 128 is the channel and the width and the height of the data. And the labels, yeah, we have 60,000 labels. So here we're just looking at the distribution and we can see that it's basically perfect. Yeah, every single class has the same number of images for every class. So it has 6,000, I can make this even a little bigger. It has 6,000 images for every single class. And when I was talking about understanding the pixel intensity, so here we're just visualizing one of the images. And as you can see, because we normalized it, the values are centered around 1 and they range from -1 to 1. And if we actually plot this, and let me make this a little smaller now, you can see that each one of those squares, each one of those numbers is 1 pixel in the image. So -1 is completely black, and then oh, we do have a couple ones here. 1 is completely white, and then everything in between is just shades of gray, and it goes from very dark to very bright. So that's basically what an image is, and that's what a computer is seeing. And if it was like colored, you'd be 3 channels. So you'd be red, green, and blue, and they would be stacked on top of one another. But it's the same idea. And then here we're just visualizing some of the images on the data set. So you can see the classes and then the images themselves. And you can see they're super low resolution, only 28 by 28 pixels. Okay, so let's talk about embeddings. So in deep learning models, they do not compare images at the level of the raw pixels, but instead they convert those images into embeddings. And those are numerical feature vectors that capture the visual characteristics of the images. So like I said, embeddings, they are vector representations of those characteristics of the images. So somehow the model is able to learn those features from the images and basically learn them into this vector representation. So the numbers that they actually make sense. They're basically they express the characteristics of the image themselves. So embeddings is a vector representation where the images are visually similar and they have similar embeddings. And the images that are not similar, they have very distant embeddings. So in this space, the images that are similar, they're going to be very close together. And the ones that they're not similar, they're going to be far away. So for example, sandals and t-shirts, they're probably going to be very far away. But maybe shoes and some bags, just because the way how they are in this data set, they're kind of like squares. Sometimes they're very close together. And then why using a pre-trained model for this? So here we're going to be using Dino V2, and training a model from scratch, it's very compute intensive. And we can basically leverage a pre-trained model that was trained on a very large data set that basically learned general visual representations from that very large data set. And we can use that for downstream tasks, and basically just doing kind of like zero-shot learning. But in this sense, we're just going to be using Dino to extract the embeddings from the images. And the output is going to be this fixed length embedding vector that is going to have 768 dimensional vectors. So what does that mean? It means it's a vector with 768 numbers. And those numbers represent basically what the image is or what the image looks like. So it's able to convert that visual representation into a vector of numbers. And it does that during training. And then after training, we can simply query the model. We can use the model to extract those vector representations. So here we're just loading the model. And by the way, we're just loading Dino from Hugging Face in this case. So auto image processor from pre-trained, this is from Hugging Face. And this is the Hugging Face model card. So also, if you click here, there's going to be like the official Dino V2 page. It's a model that was trained by Meta. And Dino V3 already came out, which is the newer version of Dino. And if you go on, let me just type so you guys can see. If you go on Hugging Face and what is it? Facebook slash Dino V2 dash base. So this is the model card for Dino V2. And basically we just got the model from here. So it's very easy, as you saw, just a few lines of code. And we load the model and we just check for the dimension of the embedding that the model has. So it produces embeddings with 768 dimensional vectors. So extracting the image embeddings, we have this function here that we load the model. We load the torch tensors, which are basically the images that we already converted into tensors. Batch size, we're going to be extracting images into basically 64 images at a time, or feeding 64 images as a batch into the model. So basically, this is what it's doing. It sets the model to evaluation. It has this all embeddings, each is empty list. And then the key thing here, especially when it comes to visual embeddings, is that um, Dino actually outputs a very large embedding representation, but we only take the CLS token. CLS stands for classification token, that is used for classification purposes. And I think the entire embedding representation of Dino is like 512 or something like that by 768. So it's quite large. And the CLS token is the last one on that last layer that Dino has learned. And the way how we remove or we're able to take the CLS token embedding out of the model, we just take from the last hidden state and we just pass these parameters and then to CPU and to NumPy, and then we append the CLS embeddings into the list and we return that. And because we can't probably load everything to memory, I haven't tried, but I think clustering wise would be kind of messy. You'd be like way too much to load like all of the 60,000 images. We actually just randomly sample a subset of the images. So we're only selecting 5,000 random images out of the data. Um, and then from those 5,000 images, those are actually the images that we pass and we extract the embedding. So just to recap, we're only getting 5,000 images and their embeddings, or basically we're only getting 5,000 embeddings. And the embedding shape, so it has 5,000 and each embedding has 768 dimensions. And then, cool, like we do that, we extract the embeddings, we save them. The other thing that we do, if we want to visualize them, because they are in this very high dimensional space, we have to reduce them to a dimension that we can visualize. So either a two-dimensional space or a three-dimensional space. Here we're going to be doing in two dimensions, and we're going to be using UMAP, which is this dimensionality reduction algorithm. And you can click here and read more about UMAP. So uniform manifold approximation and projection for dimension reduction. So it's basically a projection of that 768 dimension to two dimensions. So we load UMAP, and this is through, I believe, if I'm not mistaken, scikit-learn. Let me check. No, it's from UMAP, the library. Scikit-learn has other dimensionality reduction algorithms. But going back, we load UMAP, number of components. So here are going to be the dimensions that we're going to be reducing to. So two dimensions, the metric is going to be cosine. We choose 15 neighbors, but you can actually play with this and random states, just making sure that every single time we do this projection into a lower dimensional space is always going to be the same. And we do that, and then we just plot it. And let me make a little smaller. So by plotting, we can see that we get those clusters, and we can check the basically what they are, what they come from, like all the categories. So you can see that trousers and dresses are kind of similar here. Over here we have ankle boots and sandals, which kind of makes sense. Footwear, and you can see like footwear and dress and clothes are very, very distant from one another. And then we also have bags here that they formed their own little cluster. Um, but yeah, very, very cool to visualize this. And one thing that we found, at least one thing that I really find helpful when I'm doing the research projects, is the first thing that I try to do once I do have the data available is doing some kind of clustering and visualizing the distribution of the data and seeing how sparse or how different that data is. So a notebook like this that we're going through right now would be probably one of the first things that I do, or probably the first thing that I do once I do have the data available, just to visualize the distribution of the data and how it's similar. And then I also it basically gives me some ideas of things that I can do to improve the classification or to improve my methods. Because here we already see like, oh, cool, we have three clusters together. I wonder what I can do to make sure that the model actually learns those representations if I'm trying to train a model. Okay, I'm gonna actually stop here for a second and check if you guys have any questions. Anybody has any questions? I see that Anthony is answering people. Um, is there anything that I can talk about, Anthony? Or we're good?
I think for uh, you said for the 60K images, whether that would
Yep.
fit into memory or not, I'm pretty sure that would fit into memory. Like each of the vectors is about 4K. Like if you just choose a nice round number, like imagine that the vectors are 1,000 numbers wide and each number is represented by 4 bytes. Um, then if you just like kind of guesstimate like how big that is in memory, then it's like a quarter of a gig. And like these instances that you load up are pretty big. So like you could do it
Okay.
all in memory.
Okay. That's nice. Um, maybe that would be like a little to do for the people watching this to do. To actually visualize all of them and kind of see how the cluster is gonna be. I'm probably gonna do this after the meeting actually, just to see.
Yeah. And
Um,
then there's also like other things to play around with like the UMAP embedding. Because
mhm.
UMAP itself is a pretty interesting algorithm. It's kind of a logical extension or follow through to the TSNE and other kind of they're like graphical methods. So like TSNE is like a I forget the exact thing, but it's like it's a nearest neighbor like embedding model. So you take the points and you kind of find their nearest neighbors, and then you embed the like network into a manifold. So UMAP kind of works the same way. Like you find the nearest neighbors, and then you like look at the geometry of the network to kind of create the nearest neighbor embedding. Um, but there's two parameters that are pretty interesting, like the input metric and the output metric. So you can basically make it so that when you're looking at the data that gets embedded via UMAP, the input is like I want to compare distances using cosine distance, or I want to use the Euclidean distance, or you could do like really interesting metrics like I think they have Earth movers distance, um, or these other metrics that are just kind of harder to compute because they use a really interesting like algorithm called nearest neighbor descent. Um, so that's like for comparing input data points, and then it also has like an output metric, so you can say like I want um, points in my embedding space to be spread out according to Euclidean distance or cosine distance or like a hyperbolic distance. So they there's a lot of flexibility in like the way that you represent data using UMAP. It's a cool library. It's a cool way of representing data. So it's worth playing around and just seeing like how that changes the visualization.
Yeah, no, for sure. Thank you for that. Yeah, like I'm showing here, there's a bunch of different metrics that you guys can play with and just dive in into how they're computed. The other library that we have been using too is SpecMap. And I think it's like it has some more efficient stuff on top of UMAP, right? I don't remember exactly, but um yeah, it's another one that you can try. Okay. So keep going with the notebook. So one thing that you can do is evaluate the cluster quality, and you can do compute the silhouette score for that. If you have taken if you have taken the machine learning class, this is probably ringing bells from that class, uh, from the unsupervised learning assignment, which I believe is the third assignment. And basically, it computes a score between -1 to 1, and higher is better, which means that the clusters are more like closely tied. Um, and we got a score of 0.25 because, as you saw, they're quite on top of one another. So, but it's a little bit better than average, I guess. So the other thing that we're gonna do is we basically took our images, transformed them into tensors. We extract embeddings from them using a pre-trained vision transformer. We did some clustering on them using UMAP. We visualized the cluster, and then now we can do a similarity search of those embeddings using a nearest neighbor algorithm. And basically, we're just gonna take one image or one embedding, and this algorithm is going to find the embeddings that are most similar to that one based on some metric. And in our case, it's going to be cosine similarity. So it's the angle. And yeah, very easy. We just use scikit-learn to import the nearest neighbor library, and you can check here the parameters. So in our case, everything else was this is just the defaults, and we gave cosine similarity and the top five neighbors. And then here I just have this function that I created to plot, and we can actually check the images. I wish that I could just run the notebook. Is it still going on? Ba, ba, ba. Well, maybe I would try that later. Because the one thing that I did is every time you run the function, it, because it chooses a random data point, you get a new image, and then you can see how that um, changes. You can see how you can see how it gets like the most similar images based on that one. But every time you run it, it changes the core image. So in this one, for example, it got a dress, and those are the most similar embeddings based on this embedding. So here we're just visualizing the images, but it's actually searching through the embeddings of the image. And in our case, it's a dress, and it got a trouser, a t-shirt, a trouser, and a trouser. So it did not get the same class at all on this. And find and visualize class. Yeah, the query this news neighbor query the image with the top five most similar images, find a visualized class, sneaker top five, find images similar to a sneaker. And those are actually just visualizing. Actually the title of this is not right. Here we're just getting like images. And then here we're using k nearest neighbor to actually find the most similar ones based on similarity. So yeah, you can see similarity score 84%, 84, 84, 83, and you can see in the sneaker and you can see all of the images. And that's basically it for the notebook. And I'm not sure why it's taking so long for the virtual environment to load. Um,
You
which is
just
a shame
restart.
because
You restart
I
the
did
notebook.
I did try, but it's not even letting me to like interrupt.
What about reloading, like Control Shift P and then reload your window?
Reload the window like the host.
Yeah, just reload the entire window.
I see.
No, you Control Shift P, and then just type in reload,
Oh,
and then there's like a reload window. That second one, yeah.
gotcha. And yeah, this is the one. Okay, now it's going. Let's see if it's gonna take less than 4 minutes. Well, I'm not gonna wait too long, but it should be much faster than what it was for Laura. We still have some time. Does
You,
anybody has
you
any
wanna
questions?
you wanna double check the path that you're using for the Python interpreter?
Yeah, it's on the user.
Oh,
So
I
it's
see.
the one that is on the temp directory. Oh yeah, there you go. 35 seconds. So that's much better. And probably because we're loading a bunch of libraries and some of them are very heavy like Torch, but this is actually pretty nice. So yeah, we can just go through the notebook very fast until the point that we did um, dimensionality reduction, and then I'll run all of them, and I'll just wait here. So let me see if anybody has any questions while we wait. Um, yeah, just a question about the temp directory,
Yeah, I think you forgot to mention
the bash RC
uh
file.
yeah. Did you do the bash RC?
I did here, but I did not add to the README. So let me do that right now.
It might be good to mention that temporary directory is only valid inside of an interactive or batch session, and that if you're on the login node, then it doesn't exist, and you can default to the temporary directory there.
Yep. Yeah, I'll do this right after the call, but I'll add the basically the command to set a temporary directory into the bash RC, and then you source it. Okay, cool. He ran. So yeah, as you can see, it just queries the images, and we got the their classes, pullover, pullover, sneaker, and then you can change this parameter k equals 6, and you can get more images. K equals 8. Sneaker, sneaker. And then you can change if you like, instead of being sneaker, you can do dress, and you get all of the dresses, or you can do what's the other one? Sandals, sandal. It's fun. Um, I'll leave it. Sneaker. Leave this for. But yeah, so this is the notebook, and basically we learn about embeddings, a little bit about clustering, doing dimensionality reduction, and then using nearest neighbor to do some kind of search. So for you guys, the thing that you guys can do this week is not only running the notebook, but you can definitely try some things. So one, we tried Dino V2, but like I said, Dino V3 is out. So instead of Dino V2, you can try Dino V3 and you can see how the embeddings change and some how different you get the results. You can also try to do nearest neighbor classification directly on the embedding. So um, sometimes when we think about image classification, we think about training CNNs like convolutional neural networks or the breast nets or vision transformers, which you can get embeddings from them. But once you do have those embeddings, instead of training a linear classifier to do classification, you can also do classification with k nearest neighbor. So basically what we're doing here, for each image, we just take the most similar image based on the core image, and we just classify that way. And you can see how far away you are um, based on that. Um, and you do that on the test data, by the way. So not on the training data. And the other thing that you can do, like Anthony said, you can play with UMAP. So UMAP has a bunch of parameters, and I can go back here and I can, one thing that we can do is instead of doing 5,000, let's do like 20. Um, so it's gonna extract the embeddings of 20,000 images. And then here, instead of doing, for example, cosine similarity, let me do another metric here. So correlation, how about we do Euclidean? Euclidean. And instead of 15 neighbors, we get like 10. And then we leave that like it is. So this takes a little bit of while, just because basically what is happening, we're feeding 20,000 images into the model and we're extracting those images. But because we are on a GPU, we can see that because we are using a GPU, at least because I am using a GPU, you can see the utilization of the GPU here. And this is just a really nice thing to do, to see how the GPU is being utilized. And it's kind of oscillating up and down. Usually, really good utilization is on constant up, like 100% all the time. But like this is probably fine, especially for what we're doing. And probably what is happening right now, the reason why it's oscillating, it's probably because the batch size is small. We're only feeding 64 images into the batch, so this can go up a lot. I'd say like 256 or even 520 for each batch. But yeah, I ended up taking a minute and 80 almost 2 minutes. So for 20,000 images, that's not bad at all. And then we do dimensionality reduction. And then maybe this step I'm gonna have an issue. At least I've tried to do dimensionality reduction on a data set this size, and I had some kind of like memory issue, but hopefully, like Anthony said, it's not gonna be a problem here because the embeddings are not that big. Um, even though we have 20,000 of them. So this should take a little bit of time as well, maybe a minute or so. And then I'm just gonna run the rest, or I'm just gonna run the next one and see what we're gonna have. Oh, there you go. Very cool. Um, so we see a much more busy image, but it just reinforces the clusters that we had. And this one is just a blob. There's so many different categories here overlapping one another. Um, but yeah, kind of cool experiment. So you can do things like that as well. And you can really play with the notebook and even if you like, even try different data sets. So here we're doing fashion eminence, but there's other image data sets that you can try and you can see yeah, how the embeddings change everything. Um oh, what GPU command did I use for this? So NV top, NVIDIA top. Yeah. And you can see the how the GPU is being utilized for that. And then to exit from here, you just press Q and you exit. Another thing that you can do is like while you're running here, you can actually um, open up another window here. And if you know Tmux, then you can open up a bunch of windows the way that you like. I know that Anthony uses Tmux quite a lot. Um, But yeah, that's basically it. We're almost at time, so I'll go back to the presentation. And that's it for today. So I don't have any reminders or anything um, to talk about besides this. So I guess a couple reminders would be make sure to keep working on your research proposal drafts, regardless if you want to do the 8903 or not. I think it's a really good exercise to go through those. And I'm looking forward to seeing your PRs. So basically, I guess one thing that I can talk about, after you do finish running the notebook, what you're going to do is, like I said, you're going to copy the notebook from the embeddings folder into your users folder, and then you're going to open a PR into the project. So if I go into the project and I go into,
I merged a bunch of them in. You
oh,
can
you
look at the
already
merged
did?
ones.
Okay.
Look at the closed
Uh,
ones.
close. Yep. So yeah, here just looking at Harshal exercise 00 and 01. He added the folders here on the commits, and we already merged them. But the way how you're gonna do it, once you create your branch, you just create a PR, and then we're gonna review the PR and merge it for you. And then your name, the best thing is that you get your beautiful face here under the contributors. So I'd like to see as many people contributing to with this as possible, because doing this right now is gonna save a lot of time in the spring. And yeah, it's just a good exercise to go through. That's basically the reason why we're doing those exercises here on Pace, to help you guys with the onboarding and get up to speed before we tackle any research projects in the spring. So yeah, that's it. I'll stay around if you guys or if anybody has any questions, but feel free to drop. And next week's gonna be about information retrieval. So we're gonna have a new project, and it's gonna be the last project of the semester. So yeah, with that, thank you very much for joining, and I hope to see you guys next week.